Hello students, today I have question number 8 to 15 and 1 to 7 I have told you. So today I will take the Neet 2018 series AA, question number 8 to 15. So now question number 8. Unpolarized light is incident. Is incident from air on the plane surface. From air on the plane surface of a material of refractive index mu at a particular angle of incidence at a particular angle of incidence I, it is observed that the reflected and refracted, refracted rays are perpendicular to each other. The question is, which of the following option, which of the following option is correct for this situation? Is correct for this situation. Now first option is I equal to sine inverse 1 upon mu. Second is refracted ray is plane is polarized. Reflected ray is polarized with its electric vector, vector perpendicular to the plane of incidence. Electric vector perpendicular to the plane of incidence. To the plane incidence. And now third option. The reflected ray is polarized. Reflected ray is polarized with its electric vector parallel to the plane of incidence. Parallel to the plane of incidence. And now fourth. This I equal to tan inverse. I equal to tan inverse 1 upon. These are the options. Solution. Let this is the interface. This is the medium. This is the light ray. Incident light ray, and it has both kinds of vibrations. And this is reflected and also it is refracted. We know that in reflected rays there are only the dot vibrations. Dot vibrations. And here we have the arrow vibrations. So this is the mixture of the two, like this. And this angle is 90 degree or pi by 2. This is reflected and this is refracted. Then you can see that the reflected ray contains those vibrations which are perpendicular to the plane of incidence. This is the plane of incidence, then perpendicular to it like this. So it contains only those vibrations which are perpendicular to the plane of incidence. And this contains the vibrations which are parallel to the plane of incidence. Because the vibrations parallel to the plane of incidence will pass through the medium. And that will be the refracted ray. So in reflected ray we are having only the electric vector perpendicular to the plane of incidence. So second option is right, third is also wrong because this is not this so much, and first and fourth is are quite wrong because there is no such kind of relation. So our answer is the second answer. Second. And now question number 9. In Young's double slit experiment, Young's double slit experiment, the separation D of the two slits the separation D of two slits is your 2 mm. 2 mm. The wavelength of light, the wavelength of light is 5896 angstrom, and the distance d, and the distance d between the skin and the slit. Slit is 100 centimeter. 100 centimeter. It is found that angular width, it is found that angular width of the fringe is 0.20 degree. To increase the fringe angular width, to increase the fringe angular width to 0.21 degree with same lambda and d, with same lambda and d. The separation between the slits need to be changed. Need to be changed to. Now option is first 2.1 mm, second is 1.9 mm, third is 1.8 mm, and fourth is 1.7 mm. You are giving everything. Here we are giving the D. Solution. Given D equal to 2 mm and wavelength lambda equal to 5896 angstrom and capital D equal to 100 centimeter, so this is equal to 1 meter. The angular width theta is equal to beta upon capital B. This we know, but beta equal to lambda into d upon d. So we have this theta equal to beta upon d, that is equal to lambda upon d. Because we have to find the separation, small d. separation small d. So this is now you are given that theta and let theta dash equal to lambda upon d dash. So you find this theta dash upon theta equal to, this is your lambda upon d dash into lambda upon d. Lambda will cancel. So we have this theta dash upon theta equal to d upon d dash, or theta dash equal to theta into d upon d dash. Now you put the value. Theta is given to you. This is not so much. Angular width is 0.2. So this is 0.21, 0.20 into capital D, small d. This is given to 2 mm. 2 mm. Upon d dash is to be changed. D dash we have to find, and this theta dash is given to you. So this is equal to, theta dash is given to here, this 2.1, so much. So this 0.21. So d dash, or d dash equal to 0.21 into 2 upon 0.20, 0.21. This is so much, so this is comes out to be 0.40 upon 0.21. So this is your 1.9 something. 1.9. Moreover, whenever we have to change, we have to increase the angular width or the width of the interference fringe, then the distance between the slits must be decreased. So our right option is second, 1.9. This is now right option. And now question number 10. An astronomical refracting telescope. An astronomical refracting telescope will have large angular magnification, will have large angular magnification and a high angular resolution, and high angular resolution when it has an objective lens, when it has an objective lens of. Now options. First option is large focal length, and large diameter. and second option is large focal length, and small diameter, third small focal length, and large diameter, and fourth option is small focal length and small diameter. Small diameter. Now we have the angular magnification. M equal to F0 upon Fe. This is the formula, and that angular resolution theta is equal to this is given by the formula 1.22 lambda upon d. So this is the what first is giving the magnifying power, and this is giving you the resolution limit. So that also named by this one angular magnification and angular resolution. And you can see from here that this M is maximum when F0 is maximum. The focal length of the objective lens must be large. Angular resolution is maximum when D, the diameter of the object, is small. So for higher angular magnification and the angular resolution, the focal length of the objective lens must be large and the diameter of the objective lens must be the small. So for this we have the large focal length and small diameter. The second option is right one. For large M, F0 is large, and for large theta, this D is small. So our answer is second one, large focal length and small diameter. Now I have the question number 11. The ratio of kinetic energy. Ratio of kinetic energy to the total energy. Total energy. electron in Bohr orbit. In Bohr orbit of hydrogen atom. Hydrogen atom is, now option is first 2⁻⁻1, second 1⁻⁻1, and third 1:1, and fourth 1⁻². So you are given the hydrogen atom and there is the electron in the Bohr orbit. So the kinetic energy we know. Kinetic energy. This is equal to 1/2 kZe²/r, and total energy this is E equal to -1/2 kZe²/r. Now you can see the relation for both is the same with a difference only with the minus sign. So kinetic energy to the ratio of kinetic energy to total energy. This is 1:-1. This -1. So our option is second. So our answer is second. So this is a direct application of the kinetic energy of the electron in hydrogen atom and its total energy. So you will find that the ratio coming out to be 1:-1. And now question number 12. An electron of mass m with initial velocity v equal to v0 I. v0 greater than 0 enters an electric field. E equal to minus E0 I. E0 constant. E0 equal to constant at t equal to 0. Constant greater than 0. At t equal to 0. If lambda naught is its de Broglie wavelength is its de Broglie wavelength, then wavelength initially, then its de Broglie wavelength, then its de Broglie wavelength at time t. At time t is, now your first option is lambda naught t, second is lambda naught into 1 plus e naught t upon m v naught, and third option is lambda naught upon 1 plus e t upon m v naught, and the fourth option is lambda naught. Now the solution. Now you have the electron of mass m with initial velocity so much enters the electric field with given by this one E naught. E naught is a constant greater than 0 at time t equal to 0. Lambda naught is its de Broglie wavelength initially, then its de Broglie wavelength at time t is so much. So now we have the electric field is acting there. So now force on the electron F equal to E into E. So this is given to so much. So this is your, we take the magnitude, then this will be your E naught. Now acceleration. E equal to F upon m. So this is E naught upon m. Now initial velocity is given there, then there will be some final velocity after time t. So velocity after time t. Velocity after time t. This v equal to u plus at. We will use this equation, first equation. Equation of motion. So now this is given to be now v, and this u is given here. U is so much, v naught plus a is here, e naught upon m multiplied by t. Then v equal to v naught you take common, 1 plus e naught t upon m v naught. Just to multiply m by both sides. mv equal to mv naught into 1 plus e naught t upon mv naught. And now we know that de Broglie wavelength. We know lambda equal to h upon mv. So first we are giving this lambda naught, this so much, and from here this mv naught equal to h upon lambda naught. Similarly, lambda equal to h upon mv, then from here this mv equal to h upon lambda. So we will use these relations here. Therefore, now here we will have this lam h upon lambda equal to h upon lambda naught into 1 plus e naught t upon mb naught. Now you can see this h will cancel. You have to find the lambda, this lambda. Therefore, lambda equal to lambda naught upon 1 plus e naught t upon mb naught. So this is the de Broglie wavelength after time t. So you can see that this matches with the option third. So our answer is third. So remember here that what we are given the electric field, so just you find the force and then acceleration and then the velocity after time t, like this. Take the common v naught, then we will get this relation. Then use de Broglie wavelength and then put these values and find the value of lambda. So this is what the de Broglie wavelength after time t in the electric field of strength E naught I. Now question number 13. Question number 13 is given for a radioactive material. Radioactive material. Half-life is 10 minutes. Life is 10 minutes. If initially there are 600, if initially there are 600 number of nuclei, the time taken in minutes for disintegration. Of 450 nuclei is first is given 30, second this is now 10, third this is now 20, and fourth this is now your 15. These are the options. So now we can solve this question orally also. You can see that half-life is given 10 minutes. So in 10 minutes the 300 will nuclei disintegrate and 300 will remain. In the next 10 minutes the half of 300 will decay. So the 150 will decay and 150 will remain. The active nuclei will remain 150. So initially they are in the one half-life 300 are decayed, and in next second half-life 150 are decayed. So 450 are decayed. It means that 150 are left. So now time taken in 450 nuclei, this will be the two half-lives. So this is not 20 minutes. This is the direct answer also. Or you can solve it by applying the formula also. N equal to N naught into 1 by 2 raised to power n. Now this N naught given 600. Decayed is how much? 450. Is time taken for disintegration of 450 nuclei. So N will be how much? 600 minus 450. So this is now 150. This is the active number of nuclei which are not being decayed. So you can see this is now 150 equal to 600 into 1 by 2 raised to power 2. This will cancel by 4. So 2 raised to power n equal to this is now 2 square. So n is equal to 2. So n is what? The time t upon this, so is equal to 2 months. And this t is equal to 2t. So 2 into 10. So this is now 20 minutes. So you can solve this by the formula also, or you can do it orally also. So our option is 20 minutes. 20 minutes is the third one. Now question number 14. The 14 is given when the light of frequency 2 nu naught, when the light of frequency 2 nu naught, where nu naught is threshold frequency, where nu naught is threshold frequency, is incident on a metal surface, is incident on a metal surface, metal plate, not surface, metal plate. The maximum velocity of electron, the maximum velocity of electron emitted is B1. When frequency of incident light is increased to increased to 5 nu naught, the maximum velocity of electron, the maximum velocity of electron emitted from the same plate is B2. The ratio of B1 and B2. The ratio of B1 and B2 is, now your option is this is 4:1, second 1:4, third 1:2, and fourth 2:1. Now the solution. Now question is from the photoelectric effect, and we know the Einstein photoelectric equation. Einstein photoelectric equation. Photoelectric equation. This we know that this is equal to H half mv square equal to H nu minus H nu naught. First the frequency is 2 nu naught, nu equal to nu naught. When nu is equal to 2 nu naught, then this will be equal to B1. So we have half m B1 square equal to, this is 2H nu naught minus H nu naught. So half m B square equal to H nu naught. This is equation 1. And second, when nu equal to 5 nu naught, B equal to B2. So half m B2 square equal to 5 H nu naught minus H nu naught. So this is equal to half m B2 square equal to 4 H nu naught. This is equation number 2. Now divide 1 by 4. So this is your dividing 1 by 2. You will get this half m B1 square upon half m B2 square equal to, this is equal to H nu naught upon 4 H nu naught. So half m will cancel, H nu naught will cancel, here is 1. So B1 upon B2 is square root of 1 by 4. So this B1 upon B2 is equal to 1 by 2, or this is 1:2. 1:2. 1:2 is this one, third. So here our option is third. So this is a direct application of the Einstein photoelectric equation. Just you have to understand that the frequency is increased to 5 nu naught. 2 5 nu naught. It means that the second time the frequency is 5 nu naught. Now I will take the last question of today's question number 15. In the circuit shown, in figure, the initial voltage Vi, the initial voltage Vi, that is equal to 20 volts. VBE equal to 0, and VCE, this is equal to 0. Then value of IV. Now ask, then value of IV, IC and beta, beta will be given by. Now first option is here. First I draw the diagram. This is E. Here is B. This is resistance. This is now given your Vi, and Vi is your 20 volt. This is not 20 volt. Here this R is equal to 500. R 500 kilo ohm. And then we are having this resistance. This is now 4 kilo ohm, and this is 20 volt. This is your C. So like this we are given. The first option is IV equal to 20 microampere, IC equal to 5 milliampere, and beta equal to 250. And now second option is IB equal to 25 microampere, IC equal to 5 milliampere, and beta equal to 200. This is third. IB equal to 40 microampere, IC equal to 10 milliampere, and beta equal to 250. And then fourth, IB equal to 40 microampere, IC equal to 5 milliampere, and beta equal to 125. So now solution. You see that this emitter has been asked, so this is at zero potential. Current will flow in this one and in this one. You are given the voltage and this is given the resistance. So IB, this is your VI upon R, RB. VI is equal to 20 volts and this is equal to 500 kilo ohm, 10 raised to the power 3. So this we increase, this we make it to be a 1, 2, 3, 40, and we have increased 2. This is 400. One more. Then this is 10 raised to the power minus 6 upon 500. Then this will cancel 40. So this is your 40 microampere. So much. We have to convert this into the micro because all options are given in micro. And IC equal to your this voltage upon resistance. So this is your 20 upon 4 kilo. Kilo is 10 raised to the power 3. This we have taken, this we cancel by 5. So this is 5 into 10 raised to the power minus 3. So 5 milliampere. And now beta equal to your this IC upon IB. This is the formula. IC is your this 5 milliampere, 10 raised to the power minus 3. IB is 40 micro, 10 to the power minus 6. So this will cancel, 10 raised to the power 3. So this is equal to 5000 upon 40. This will cancel, 4, 8, 4 1 is 4, 4 2 is 8, 5 2. So this is 125. So what IB is 40 microampere, IC is 5 milliampere, and beta is 125. So fourth option is right. Our option is 4. So this is what the value of IB, IC and beta from the given data in this figure. So now then we find the values of all this. So these are the question number 8 to 15 for today. So you have seen that the questions from the different chapters are coming here. So try to understand them and watch the full video. Thank you very much.